We'll have more joining pretty soon. There's Nathan.
Hi, good morning.
Probably find it in YouTube.
Right,
Yeah.
true. I don't know, but it's involved with CoStar.
CoStar, okay. We'll look it up afterwards.
JPL CoStar, and that's capital CoStar, so it's an acronym.
Yeah, I think there's a website for, I can put it in the chat log.
Okay, so is it CoStar like one word?
Yes.
Yeah, okay. Let's see. That's it's a website, but it also has a lot of the videos, the background videos, and
all right, we can check that out.
Yeah, it's a fun project.
You're gonna get us all excited after this, and then we're gonna go in there, right? Trying to check this out. Yeah. We're very happy to have you, by the way, Carlyn. Very happy to have you.
Yeah, thanks for organizing. It's
that was Alejandro's doing, and the team.
Yeah, thanks, Brian.
I just sit back and send emails out. That's my job.
Cool. Well, yeah, thanks for getting in touch, and Alejandro, thanks for organizing. Maybe we'll do a couple minutes.
Yeah, we'll wait for some more people.
Okay.
Yeah, it was a team effort. This is our first virtual talk session, so to speak,
You're a
professionally.
trailblazer. Trailblazer. You're the first one.
Oh,
So
cool.
we're testing
Yeah.
the waters today.
And
All
you're
right.
the first guest speaker. How about
All right.
that?
So I'm guinea pig today.
No pressure. No pressure.
Yeah.
Yeah, it's fun. It's fun. So yeah, Alejandro has told me so much about you guys, and it's it's great to meet you all, even virtually. But I'm inspired by how motivated everybody is, and I yeah, looking forward to.
You also you also volunteered to help out our team as well, to be a mentor, of
Yeah,
course, virtually. And
I was hoping
so
to
that's
join you
why
guys.
she's here as well.
Yeah.
We need more of that. We need more of that. That's good. Thank
Yeah.
you.
Yeah, Alejandro told me about the April contest, which I think, with the current COVID-19 situation was rescheduled, hopefully, or.
Yeah, actually, it's been rescheduled, but into a new season.
Okay.
We're going to still follow the same concept. However, competing in person is still unknown, but they're giving us some virtual tasks for us to compete. So we'll send you information about that as well, because
Oh,
that's coming
interesting.
up. Yeah.
Okay. Fantastic.
Yeah.
All right. So it's 5 after, and yeah, maybe I can just get started.
Okay.
And,
I believe so. You think, Mr. Alonso, should be
Yeah, we
okay?
have right now we have 12 people in attendance, right? But yeah, if you want to get started, I think people may join in as they remember. Oh, wow, it's Saturday, it's Saturday, right? So some people may be mowing the lawn or something, I don't know.
Okay.
Good.
That's what my neighbor is doing.
Let's see. I guess right now I can share my screen and see how.
Yeah.
While people sign in.
I'm gonna turn my mic off, and I think everybody should turn themselves so that might be helpful that way, except for you.
Okay. Great. Okay, so I think that's sharing the screen, and
Yeah.
so yeah.
I'll introduce you, and then you should be able to take over. Do you hear me?
Yeah, I hear you. How do you hear me?
Okay, so I'm going to talk right now. Hi, everybody. This is our first virtual talk, and Ms. Carolyn Lee is very kind to submit her time to give us a talk and talk about her interesting work that she does at JPL. She's a good friend of mine. She knows you as when I talked about you guys, and I think she's seen some of you over there at the JPL Invention Challenge. You guys compete there, and so from a distance, you don't see her in the crowd, but she's there, and other friends of mine. So I'm happy and honored to have Ms. Carlyn Lee to give her presentation and her work and sharing her work. So go ahead, you can take over.
Okay. Hi everyone. So I'm Carlyn, and I'm a software engineer at the NASA JPL. I earned my bachelor's degree in computer science in 2011 and my master's in 2012 from Cal State Fullerton. I started as an intern at JPL in the summer of 2012 while I was finishing my master's, and then I became an academic part-time while working on another master's degree in math. But when a position opened up for me, I jumped on the opportunity to work full-time as an engineer. So I've been a software engineer at the lab since then. And yeah, I think it's also cool, and you know, you guys are you know, lucky that you are pursuing an interest in robotics now, and you get to work with Alejandro and Francisco and such a great team. And you know, when I was in high school, it wasn't clear to me that this was a career path I wanted to pursue. But you know, I was fascinated with technology. You know, when I was in high school, and you know, around you know, junior high was a time when, you know, the peer-to-peer networking applications made you know, pirating music and sharing music you know, possible. And so this was also the time when you know, massively multiplayer online games were becoming you know, more advanced. So yeah, a lot of that inspired me, and you know, maybe this whole work from home quarantine situation inspires you to learn more about the technology we're using every day. So yeah, I think it's great, especially if you know you already want to pursue a career in STEM, that that you're doing this, and you know, either way, like you know, everything you learn from this experience is going to help you out in the future. So with that said, you know, I'm here to talk about wireless networks and how we use wireless, you know, technologies to communicate to spacecraft out, you know, on different planets and different space. And it'll, you know, all those things tell us more about the universe in which we live. And here we go. So I'd like to start this discussion with a background on how wireless communications work. I think this video does a great job at explaining some of the basic concepts of wireless technologies, and maybe you're already familiar with it. You know, some of these technologies talked about in this video can be a good way to refresh that knowledge for our next topic on deep space communications. So let's see if I can.
How does wireless work? Wireless communication develops at high rate. Wireless, however, is not a new invention. In 1864, Maxwell proved the existence of electromagnetic waves. In 1887, Hertz sent and received wireless waves. In 1895, Marconi sent radio signals over more than a mile. In 1920, there was the first commercial radio broadcast. In 1930, BBC began television experiments. In 1974, FCC allocates 40 MHz for cellular telephony. In 1982, European GSM was established. This is where we can say that modern wireless communication began. Where can we find wireless now? It is used mostly for broadcasting or communication in radio, television, satellites, Wi-Fi, and mobile networks such as 3G, 4G or 5G. But wireless can be used not only to transmit the data. For example, radars are based on waves. Where does exactly wireless start? First, we need a device called a transmitter, which has an antenna. Inside transmitter, there is an oscillator that is connected to the antenna. Oscillator creates signal that propagates through the wires to the antenna. Antenna is a conductor, so signal propagates further towards the end of the antenna. Oscillator generates signal continuously, and antenna radiates that signal into the air as an electromagnetic wave. Signal in the antenna is an electric current, while the propagated signal is a wave. Depending on how fast signal is changing, antenna radiates signal of different frequencies. These frequencies can be used for different purposes: radio navigation, maritime mobile, radio location, broadcasting such as FM radio, mobile communication, ISM band where everyone can transmit, satellite, and space research. In order to communicate using wireless, we need more than just a transmitter with an antenna. Signal radiated by the antenna goes into the channel which transports the information and finally reaches the receiver. In order to capture the data, a receiving antenna is required, which intercepts the radio waves and converts them back to the current. Transmitter is more than just an oscillator. We don't want to send constant sine wave, but rather have some digital data to transmit. This data is encoded, which means additional bits are appended. This makes data recovery easier in the receiver. Transmitter cannot send zeros and ones directly, and that's why they are mapped into symbols, signals with different frequencies and amplitude. In the end, signal is modulated in order to use current frequency designed for a specific system. There are several ways how information can be included in the signal. Let's assume we want to send 6 bits. 0.
Okay. So that was just some introduction on how wireless communications work, and we look at ways to propagate the signal in in space, and then transmit and or receive those signals and turn them into ones and zeros. And there are so many ways to ways to do that, and that's basically what we're doing for deep space communications. We're inspired by these terrestrial networks to communicate with an orbiter much further out, and of course there are many challenges. So at JPL we use the wireless technologies described in that video, and I can put that in the chat log. I can put, or if you have a chance to visit this website, there are more details. And often in deep space communication, we're inspired by this technology that we use every day over terrestrial networks. There are many more challenges involved to communicate over far distances. For instance, we have extreme loss of power over interplanetary distances, and we're also limited by the power and mass availability aboard the space probes. So at JPL, we come up with engineering solutions. It takes some creativity and good tool set of other engineering capabilities to overcome these challenges. So eventually, though some of these solutions we come up with at JPL also come back and inspire advancements to the terrestrial wireless communications and networking technologies that we're using right now. So JPL monitors Earth using a suite of Earth orbiting satellites that return data about our oceans, air, and land. The Orbiting Carbon Observatory 2, OCO2 is what we call it, that we see here, is an orbiter that flies at an altitude of about 700 kilometers. So it's about 400 miles, more than 400 miles, and it completes, a near polar orbit every 100 minutes, and it repeats that every 16 days. So, it's got a good view of Earth, and it's collecting data that needs to be relayed back to us. So typically, these Earth observing missions use the NASA's, it's called the Tracking and Data Relays Satellite System, or TDRS, TDRSS. And TDRS is a communications relay system, kind of like, you can think of it as a space internet, it's for low Earth orbiting spacecraft, and it's the link to control and data processing facilities on ground, and the communication with TDRS is facilitated with a ground station in New Mexico. It's called the White Sands Complex. So you can read more about TDRS at this website, you can do a Google search on TDRS, and we'll bring up more information about that. So What about how do we communicate with spacecraft even further away than from these Earth observing probes? Well, yeah, we use the Deep Space Network or the DSN. The DSN consists of 3 facilities spaced equidistant from each other, approximately 120 degrees apart in longitude, all around the world. So these sites, you may have heard of Goldstone, California, out by Barstow. There's a site in Madrid, Spain, and another site in Canberra, Australia. And the strategic placement of these sites permits constant communication with any spacecraft as our planet rotates. And these antennas are large enough to enable communication to, a rover on Mars, or a probe exploring, Saturn's moons, or we'll talk about this here. The DSN antennas are extremely large. There are several 34-meter antennas and 70-meter antennas at each DSN site. So these enormous antennas enable us to reach out to spacecraft millions of miles away. The larger the antenna, the stronger the signal, and the greater amount of information the antenna can send or receive. So we try to make use of the wireless communication solutions that we discussed earlier, the ones that we use every day to enable communications with links far away, to faraway spacecraft. On the left is a graphic from a website, eyes.jpl.nasa.gov. And that's something you can explore. This shows some telemetry data from different missions received at the antenna as radio waves. We have some visualizations on the different ground antenna sites at Madrid and Goldstone and Canberra. So on the right, this is a fun photo of me next to the 70-meter antenna at Goldstone. So I'm standing outside the perimeter, but you can see that the doors, there's a kind of a room underneath the antenna base, and there's some entry points there, and that's about, I don't know, normal size of, door entrance. And I'm standing a little bit closer to the camera, but this is actually an antenna we use to communicate to interplanetary probes. Maybe after the COVID quarantines, you can go and they do permit some visits at this site, and it's pretty cool to see. So yeah, that's the 70-meter antenna at Goldstone. And so as an example of what we can do with the DSN, at Cassini's end of mission, so the Cassini space probe we see here, the spacecraft had traveled a total of 4.9 billion miles. This distance includes 2.1 billion miles a trajectory from the Earth to Saturn. We're still able to achieve data rates that vary between 5 bits per second to about 250 kilobits per second. And while that's not such a great data rate compared to our internet connection we have now, we're getting tens of megabits per second. It's really a great advancement for what we can achieve at such a far So, additionally, we have one of our best known missions, which is the Curiosity Mars rover. And Curiosity has been operating on the surface of Mars since 2012. It has a few different antennas to communicate to Earth. And while Curiosity is roving on the planet, it's communicating with the Mars Reconnaissance Orbiter through something called a UHF antenna, an ultra high frequency antenna. And it's communicating directly to the DSN by means of a high gain antenna. So the Mars Science Laboratory, while it was in cruise phase, communicated with a low gain antenna. I wish I had this picture had a better view of the antennas, but you can visit this website for more information on the antenna systems. The landing phase for MSL was also supported by the DSN. There was a series of maneuvers that were autonomously enabled to land Curiosity on the Martian surface. And I think maybe you've seen that video on the 7 Minutes of Terror. We had to address the interplanetary distance and the time, the light time we needed to receive a message from the rover once it landed, and it took about 7 minutes to receive a message from Curiosity to know that it successfully landed on the Martian surface. This is something that was supported by the DSN. Here, when I started at JPL, I went and I explored all of lab, and you probably, I think you also had a chance to see the gallery in the Mission Control Center. So this facility manages space flights, usually from the point of launch until landing, or until the end of mission. And staff of flight controllers and other support personnel are in there monitoring all of the aspects of the mission, using telemetry and sending data commands to the vehicle using ground stations. I think when you came to visit, the Curiosity rover may have been out in the Mars yard. I think maybe you had a chance to see what it was like. There's a photo of me with the Curiosity rover. My role at JPL as a software engineer is to help design the communications links between the spacecraft and ground. So given the orbiter trajectory and some mission control objectives and other factors, maybe occultations by other planetary bodies or other, what do we need in our communications stack to meet the goals of the mission? Also, when should we schedule antenna tracks to send and receive data so that we're efficiently, communicating with the spacecraft, at optimal times? Some research I was lucky to get involved in is the study of the Mars Communication Relay Network. So I worked with a team to develop software which used models describing the link capabilities between a Mars rover and other Mars orbiters. So Mars Reconnaissance Orbiter, for instance, or Mars Express, or And we try and create a deep space internet, basically, where that your rover or your science experiment on Mars communicates the data through a network of orbiters direct to Earth, where we can analyze that data. So our software takes into account this, the durations when the orbiters are in view of the science instruments and the ground stations, and to find a route to communicate that data. So when humans finally land on Mars, we'll have a way to support the science on Mars by enabling communication coverage to Martian operators. So another challenge I had a chance to work on was to use software simulations to for optical laser communications channels, and that's something that will we'll be using to demonstrate the capabilities of deep space optical communications on the Psyche mission in 2022. Psyche will explore some asteroids in deep space, and we'll also have a deep space optical terminal which uses laser lights to communicate directly to Earth, and we'll be demonstrating the capabilities of that. It's supposed to, we're expecting it to communicate data about 10 to 100 times faster than normal, our conventional means, typically through RF. So I was also involved in setting up the communications relay network for the DARPA Subterranean Challenge. The goal of this work was to rapidly map, navigate, and search underground environments. And JPL is interested in doing this work for robotic exploration of the Moon and Mars. The website is here, and I don't know, how did the videos how did the videos turn out?
We were able to see that. Yes.
Okay, so let's I think it was maybe this one we can watch. I think it's not
Starting mission.
oops.
Hello, this is Team Co-Star,
We are researchers and engineers from all around the world.
representing 4 institutions,
NASA JPL, Caltech, MIT,
and KAIST.
and we research and develop collaborative, subterranean, autonomous, resilient robots. We are based at NASA's Jet Propulsion Laboratory, where we develop advanced technologies that can explore subterranean environments.
City expansion and rising urban populations mean that we're not only looking to build up, but also to build down.
This requires new technologies to map and explore the world beneath our feet and overcome the very specific challenges these environments present.
Difficult access,
Poor visibility and communication.
Unpredictable terrain.
Finding solutions to these challenges will benefit everyone working at subsurface levels, including first responders, the mine rescue community, and disaster relief agencies.
With that in mind, we are building the next generation autonomous subsurface explorers.
Unmanned robots that can navigate the most inhospitable environments.
Which is why we have entered the DARPA Sub-T Challenge.
This competition aims to explore innovative approaches to mapping, navigating, searching, and exploring complex underground environments.
To take on this challenge, we will be using a diverse group of autonomous robots,
Ranging from unmanned ground vehicles to autonomous drones.
They will employ state-of-the-art localization and mapping solutions to explore the target environment.
Accomplish a number of set missions and relay the information back to us.
The missions are tough, First, our autonomous machines have to stay below ground for an extended period of time
and navigate a course that is between 4 to 8 kilometers long.
Along the way, they have to locate a variety of artifacts that have been left in the tunnel.
These include a backpack, fire extinguisher, cell phone, drill, and most importantly, a survivor.
When the mission is complete, our robots need to communicate their data back to a base station located outside the underground network.
And they have to do all of this with absolutely no help from us.
Team CoStar is proud to put its ideas to the test in the DARPA Softie Challenge. The challenge is incredibly difficult.
It takes place over the course of 3 years.
But the challenge for Team CoStar doesn't end here.
Today, we're exploring the subterranean world of planet Earth. Tomorrow could be the moon, Mars, and beyond. We are Team CoStar. Thank you for watching.
Nice.
Yeah, so you know, I was lucky to have a chance to work on robots with some friends, my friends, and you know, we went out to the mines at Eagle Rock to test out some robot capabilities, and yeah, this was oh, there we are. Okay, I think that concludes the talk, and yeah, let's try and yeah, we set up our testing environment in a cave in Eagle at the Eagle Mine down in San Diego County, and you know, we were able to you know, experiment with the robots and the communication systems down there, and it was, you know, it's a great technology challenge, and you know, it's a lot of fun. So that said, I think just I guess I can answer questions, or you know, maybe.
Well, I want to make a comment. For DARPA, whoever is not familiar with DARPA, is a government agency that actually it's all over the world, and it provides funding for any kind of research that is very unique and advanced. So that's where the money is. There's a lot of money invested there through the government, and it's worldwide, but mainly, of course, in the United States. Without them, we cannot, you know, explore all these different sciences, and you know, there's all kinds of, I guess, categories that DARPA supports. Not just robotics, but everything else, from the armed forces, mainly the armed forces. That's where it derives, and to the public sector, and the public and to the private sector as well. So just wanted to point that out about DARPA. And there's a lot of fundings, and there's DARPA also for inventions, any kind of invention. However, they really do a great job in manipulating and acquiring the invention, because they'll you start this or your research, and they can pull the plug right away whenever they feel like it. So you have to be careful as well. But as long as you show progress, they'll keep putting money and support you. And I've seen a lot of projects do very well, and I've seen other projects, they get their funding pulled away. So, but it's a great resource to start with. I think DARPA is also investing in students, just like junior high and high school students and college students for robotics. So we'll keep an eye on it for us to come because it gets very, very interesting. Of course, now that we have a good source of mentors, we're able to support that. So hopefully, when the moment comes and there's an opportunity with DARPA, hopefully we can jump on it.
So DARPA is all STEM driven, right? It's all STEM driven.
Yeah, yeah.
So
STEM
scientific.
driven,
Yeah, good.
any
All right, great
science,
program.
any
Great program.
technology,
Hmm.
and beyond. And then there's the private sector, government sector, where those are where they call it black projects, so to speak.
Hmm.
Uh, uh, Require a lot of, I guess, clearance, and there's a number of levels of clearance when you're involved with the government, especially in military.
There are a couple questions on the chat. If you want to look at them, maybe you can answer some of those. You don't mind, Taylor?
Yeah. This is a good question. How did JPL decide to use laser for communications for Psyche 2022? So I think there are a few reasons why we're moving from RF radio frequency to optical. As we have more and more missions that we're keeping track of, we use more of the we need more spectrum for the communications links to support everything. So we're looking at higher and higher frequencies to support missions. And laser or the optical spectrum is another avenue we can use to communicate with the probes. Am I explaining this well? And so laser communications is just one more way to provide the spectrum and the bandwidth that we need to get science data from the orbiters and send messages out there as we need to support more and more orbiters. I think we selected Psyche, so it's Psyche, and I put that in the chat log. So I think maybe the reason we selected Psyche is because the launch date would coincide with the development of the terminal, the optical terminal for development for deep space. So we're expecting that by 2022 or 2023 timeframe that we'll have a terminal that we can mount on the probe within the mass and power capabilities or limitations that that it requires, and Psyche may be the probe that can support that by that time frame. So did I answer your question?
I hope so.
Okay. Yeah, thanks. Thanks for asking that.
I want to add some information about when you started talking about Curiosity 7 Minute of Terror, when you communicate with the DSNet network and you send a signal, and that signal gets routed to the orbiter. And when it enters the atmosphere, you lose communication. that's why they call it 7 minutes of terror. However, there's been a new technology, and I think it was used on InSight when InSight landed another Mars mission uh, several months ago, I think close to a year now. They use a CubeSat, which is a miniature satellite, and the acronym for that CubeSat was MARCO. And however, it reduced the time of communication by 5 minutes or so, almost 2 minute relay miss. I don't know if you knew that, Carlyn, but so based on Marco, I was fortunate enough to work on the new version of that CubeSat called Iris. And Iris is a modification of Marco with better technology, or just it was an experiment, which that experiment was successful, and now we're improving that prototype, that little CubeSat, and I was part of that mission. So hopefully, CubeSat is going to be used, Iris is going to be used on this new Mars mission that is arriving in February. And so I just want to point that out, that 7 minutes of terror now is reduced to probably 2 minutes, but it's always been 7 minutes of terror. And I don't know if you guys haven't seen the video, but you guys should Google it. And it's very dramatic. JPL does very good in dramatizing their missions. It's very well done, very well done. So hopefully you guys get to see that.
Yeah, I have a link here, and guess I could put in the chat log as well, or maybe I can send you the slides and you can disseminate them to the email group, or I think they're all, they have all the links. But I have so yeah, as Alejandro pointed out, there's CubeSats now are seemingly the next generation of deep space probes. We can make these satellites smaller and smaller, and there are some challenges with communicating to Earth, and Marco had, because it was much smaller than a normal space probe, it had an interesting design on an interesting antenna design where it had a flat panel that opened up, and on this panel were small reflector rays which mimic the size of a larger antenna, and that was one way to work around the size, the mass and mass constraints of the mission. And Alejandro, do you know if there's any plans to try and communicate with Marco again? I think the tech demonstration went well, but then there's also, I think, maybe another opportunity to try and reach it. Right?
I don't know. I believe the life expectancy of these small satellites is very, very short. So I don't know if they're going to be using the same ones when the new rover comes on, lands. But I believe they're going to send a new set of CubeSats, and they come in pairs. So for them to communicate, I think they came in pairs because they made one redundant just in case one fails. The other one will capture information and send it to the DSN, relay it to the DSN. So I'm not sure, but I believe it's a short lifespan with these CubeSats. So it depends, and the technology is growing right now. Colleges, even high schools have attempted to do CubeSats, but a lot of colleges and then universities have done CubeSats. And it's still ongoing technology. because they're trying to make it robust. It any micro dust, or not micro dust, but like very miniature rocks, if anything hits it, it destroys the whole mission because they're so small. Think of it as a size of a shoebox. That's how small they are. And then, of course, they do have um, solar panels, and they extend. However, the body itself is the size of a shoebox, and then miniature sensors as well, transmitters, receivers, and so forth.
Yeah. So as the spacecraft gets smaller, you're presented with a new set of challenges, and you get to come up with more creative ways to work around them. So if you get a chance to work on a CubeSat, it's a great opportunity to get involved and to learn about these technologies. Practice some creative muscles to think of ways to put these devices on small space probes, send them out into space. Like Alejandro said, there's there's efforts from universities and high schools to build these small CubeSats, and they're really it's really amazing how how small we can make these things.
Do you know if I have another question? Do you know if CoStar is still planning to continue their research during this COVID-19? What other what plans do they have for the for from now on?
Yeah, so CoStar. So I think there may be some rescheduling attempts for the DARPA challenge. There's still one more round of another contest round, and that may be postponed. But there's still a virtual environment which we're developing our core autonomy packages around. So development is still happening, and the research is still happening, and it's all DARPA has provided a virtual environment to support it. So once we're things are back to normal, we can actually run the experiments and go back out into the field and test these things. So yeah, it's also one question here. I see that the Iris CubeSat draws around 35 watts. Is that just powered with solar panels, since it does not draw that much power? Oh, yeah, that's an interesting question. Yeah, it seems like solar panels can support that, right? But there's also typically on board, also power supply. But yeah, you're right. It doesn't need that much power to draw. Well, you have to allocate that 35 watts accordingly. So you think of your science missions, your objectives, and then also communicating direct to Earth. Yeah, I think, although maybe Alejandro, you can answer this a little in more detail. Is it?
Yeah, 35 watts seems to be a lot, but you can only store so much power in those CubeSats, and it can only take so much. So the larger the solar panel, the more it can take, and then you have a battery that can store that that power And if you have a source that can store that power, then you're in good shape. So for CubeSat, you're limited, and that's why the designs need to be robust, because you have to deal with the environment as well. Because if it gets too cold, your instruments are going to freeze, and then they're not going to work. So they have very little protection, shielding. You have radiation you have to deal with. You have to deal with the sun, heat, and then you also have to deal with the low temperatures.
Yeah. So
The extremes you have to deal with.
something like the Curiosity rover has a RTG, a radio isotope thermoelectric generator to supply its power. But I think maybe it does need something like this to achieve all its science goals. But maybe something like a CubeSat, doesn't need that much to satisfy the mission requirements. Yeah, I think solar panels are one thing that it can use to generate that.
Yeah. Also, I want to point out one neat thing about the solar panels, and JPL has, I guess, been very efficient in terms of making these solar panels very large. However, how do you put them in a compact piece of equipment? And I just want to point out that they use a lot of technology from origami. And origami is as you know, is folding of and making miniature things and a lot of folding. And so we do a lot of folding in terms of antennas and solar panels. You'd be surprised what you can fit in a very tight situation, but they have to expand in a certain way. And if one thing goes wrong, the whole thing does not open.
Yeah, and there's a lot of autonomy driving that, right?
Yes.
Yeah, I'm posting a video here of the 7 minutes of terror, and yeah, the landing operations, is one way, one sequence where autonomy is driving this, and so many things can go wrong in that deployment. Yeah, it was. It was when people received, or when the folks in mission control received the signal that Curiosity had landed, everybody was happy, and I think there are a lot of videos of the landing too, where you see people like celebrating and even crying because it was so yeah, it was such a relief, and it was good news. So so we're at approaching noon. I think I can email you the PowerPoint slides. I think the links are really they're fun to read, and it's a good way to kind of explore the deep space network capabilities, and the importance of communication systems in robotics and deep space exploration. So yeah.
Anybody else have any questions before we?
Who regulates the amount and type of satellites that are launched in order to prevent overproliferation in space? Okay, well, as in the communications area, I think one It's a collaboration of different organizations. So the FCC, I think, is somehow involved for at least the communications aspect. So, they have to allocate the spectrum for the communications to happen. So that's one thing. And there's also, concern about space debris. I think there are some really strict regulations on how the missions are designed, especially CubeSats, so that when they re-enter the Earth, they'll disintegrate in the atmosphere, or there are a lot of things like that, and so it's really a collaboration and negotiation between different organizations, and NASA is involved, the FCC is involved, and there are a number of groups that discuss this and negotiate around it.
Yeah, other space agencies around the world.
Yeah, ESA and JAXA, and yeah, so yeah, that's a really good question. Oh, okay. Sounds like Irvine High School also launched a couple of CubeSats.
Oh, wow.
Interesting. Yeah.
Yeah, I would have to read more about that.
Yeah. Wow, thanks so much, everybody. I hope to meet you all sooner than later after this, and yeah, it's definitely an honor to talk to you about this.
Thank you so much, Carlyn. We appreciate your time, and
Oh.
got something out of this, and hopefully get inspired. And that's pretty much my goal, or our goal. Dr. Alonso and myself pretty much think the same in terms of providing information to the kids, either in technology or what have you, experiences. So thank you so much.
Open the options for everybody so people see what they can go into later, right? So,
Yeah.
Being exposed to a lot of different things is always good. So
Yeah.
We love it. We love it.
Yeah. Thanks, everybody.
So we hope to see you part of the mentoring program.
Yeah, I'll get her more involved.
Hopefully when we open up. I mean, we need to open up. So
yeah.
We'll see how our robotics program, First Robotics, how they inform us. But at the moment, I think there's a couple of missions that we have to do with First, but at the moment there is not a one-on-one. They were planning to do something like that, but in a shorter version, like maybe a couple of, like 10 teams meet or what have you, and no audience. So, but that's still in discussion. I don't think it's thought out really well, but so in the meantime, we'll do a lot of virtual activities. So we'll get you involved.
Okay.
They're doing it with football and basketball, right? We can do a bubble too.
Yeah.
So.
And in the meantime, you've got a wealth of information on the internet. The JPL website is great, and it'll be sooner than you know it.
Everything is going to work out, so we're good. Thank you.
Thank you, Carlyn.
Thanks.
And we'll invite you on other projects that we work on, and also the virtual talks. So I plan to have, we plan to have more virtual talks. So I think I have 11 total. Hopefully, we'll invite you to those as well.
Great.
Some
of the alumni are going to present as well.
Okay.
All right, everybody. Thank you again.
Thank you so much.
Have a good weekend.
Bye-bye. You too.